I am Seema Sharma, the coordinator of this program. Dear Dr. Arun Kumar, IQSC coordinator, HOD of Physics and Electronics in College Patna, India. Other colleagues who are also here to listen this, to hear this lecture, and distinguished speaker, Dr. Kale, Dr. Girish Kale, and my participants. So this is the session which will be engaged by Dr. Kale, and I would like to welcome him on behalf of the college, on behalf of our state, on behalf of all the participants. A very warm welcome to you.
Thank you.
Dr. Girish Kale is reader in solid state ionics, Director of Postgraduate Research Studies in the School of Chemical and Process Engineering at the University of Leeds and a Fellow of Institute of Materials, Minerals and Mining, IOM3 UK. Dr. Kale's research interests broadly encompass materials chemistry and applied electrochemistry. More specifically for the development of greener and efficient processes, which is the call of the day, for functional nanomaterial synthesis, their characterization and application for the development of electrochemical devices, such as gas sensors, biosensors, sensors for metallurgical processes, alloying and refining, novel cathode and solid electrolyte materials for SOFC, experimental determination of phase equilibrium and thermodynamics of ternary and higher order oxide systems over a range of temperatures employing solid state EMF technique and novel refractories for glass making processes. Dr. Kale has strong research collaboration with leading academic institutions in the UK, EU, USA, Singapore, as well as leading industries in the UK and India's most notably the Reliance Industries Limited, Navi Mumbai in Mumbai, India. Dr. Kale has been a Max Planck Foundation Distinguished Fellow at Max Planck Institute for Solid State Research, Stuttgart, Germany. He is the recipient of the ASM IIM Lecturer Award from the American Society of Metals International. Dr. Kale has 4 patents to his credit, over 130 research publications in peer-reviewed journals, and over 80 international conference presentations in Europe, USA, Japan, Singapore, India, and China. He has given over 30 invited talks, plenary and keynote lecture at international conferences around the world. He has supervised 25 PhD students and over 40 masters in engineering and science both, final year research projects. He has been the associate editor of the International Journal of Applied Ceramic Technology and key reader of Materials and Metallurgical Transactions, Bead. Dr. Kale has been the chair of symposium on several occasions at the international conferences organized by the American Ceramic Society, the Electrochemical Society USA, and the Material Research Society Singapore. It's a matter of great privilege for me to welcome you and to introduce you in front of all the participants. And to add, I have been very much fortunate and lucky to be associated with Dr. Kale for about a year, as far as or more than a year, maybe more than a year. And we have been collaborating, working. One of my students is also working under him, and he's supervising also many of the problems, and we are always in contact, and we are trying for collaborations also. So thank you very much, everyone. And now I am just giving this session over to Dr. Kale.
Thank you very much, Dr. Seema, for your kind introduction. And I appreciate inviting me to this Zoom meeting organized by the ANC under the FDP program. Okay. I will try to now share my slides with you. Bear with me if things go wrong, because I'm used to Teams. I'm not very much used to Zoom. So bear with me for a second. Can everybody see my slides?
Yes, yes, it's very much visible.
Okay, good. So that's a good start. Because technology can sometimes play games, you see. So, okay. So my talk today is on synthesis and characterization of nanopowders of functional oxide materials, employing a novel alginate method that we have developed. And I'll try to take you through the journey that we have been using this particular process for synthesizing different materials with some functional application in mind. So they are not randomly chosen, but they have been chosen with a purpose, with an end purpose. And in the process, we are also learning, still learning, about various aspects of this particular method of producing nanoparticles. It appears very facile, simple on its face value, but on the molecular scale, I think, or atomic scale, or at the ionic scale, it appears to be challenging to find out, how this process works. It works like a dream, which you will see in a short while when I go through my slides. And yeah, I'll try to take you through the journey, which is now about 5 or 6 years now since we have started using this particular method. So the outline of my talk is shown on this slide. I'll just give you a general background of the alginate process, then go through specific examples of application of technique for the synthesis and characterization of oxide nanoparticles. Starting with some simple binary oxides, leading to some more complex towards the end of the talk, multi-component oxide materials. And then finally draw on some conclusions, maybe share with you our future directions, and a message to take home before acknowledging the various sponsors for this research journey that I have been on, or we have been on together with my postgraduate research students and postdocs. Okay, so there are various methods people have attempted to prepare nanoparticles because nanoparticles have attracted a lot of attention worldwide for their special properties that they deliver due to the nanoscale. And therefore, many researchers over the past have looked at various methods of producing nanoparticles. Some of these are listed here. And the last one on the slide, or the list of on this slide, is the alginate process that I will be telling you a little bit more about. I won't go into details of the other techniques because of the lack of sufficient time, and I think it is well documented. Some of these techniques are well documented in the literature. So I won't go through the details of all the other techniques. I'll just focus on the alginate process itself and its utility value. So why oxide nanoparticles? Oxide nanoparticles have found their way into a number of applications, such as electrochemical and semiconducting gas sensors as a sensitive material, gas sensitive material. in biosensors for measuring the analytes in the that are of importance for the biological processes. Laser communication. Now, some of this work we are also involved in, for example, in gas sensors, biosensors, laser communication. I've got a research project with one of my colleague, whereby we are looking at manufacturing optical waveguide for optical communication and developing sensors. So I'm involved in that as well. And nanoparticles have found their way into these devices, optical devices, because they are non-invasive, essentially. Materials for sensors for metallurgical applications I've been involved with. Electrical resistance tomographic sensors for monitoring multi-phase flows. Catalysts, again, nanosize or nanoparticles. They offer high surface to volume ratio, and therefore are very active and therefore have found their ways into catalysis. Some of these processes here that I have, or the applications that I have just gone through, also are in some ways related to the surface activity of the materials used in different applications as a result of nano sizes, or the particles that are incorporated in the devices. Electrodes and electrolytes for SOFC. Batteries, again, it's a very hot topic at the moment. Batteries for energy storage and energy production or delivery purposes. And finally, electroceramics for sensors and actuators. So these are some of the applications that we are focusing on as a result of the nanoparticles that we are making. We have made some of these nanoparticles for various applications on this slide. And I'll share with you some of the information when I go through the slides. Okay, so what is alginate, or where does it come from? So we are all talking about the environment and circularity of the material, to maintain circularity of the material. So the alginate, sodium alginate particularly, is a very big industry. It is in about a few years back, if I take you, I got this data from the reports where it is recorded as a $6 billion industry, particularly into food, pharmaceuticals, and cosmetics. And this sodium alginate is a very cheap material derived from seaweeds. So these are the seaweeds which you find normally in the oceans. There is a forest of seaweeds, if you are not aware of, under the ocean. And that maintains actually balance, ecological balance to some extent, or to great extent in the nature. So sodium alginate is a part of the seaweed, and it is extracted from these seaweeds for food, pharmaceutical, and cosmetics industry. So this is the purification chart that is produced. There are two different processes yielding two different types of products: calcium alginate process and alginic acid process.
Excuse me, Dr. Kale.
Yeah.
The second one where you have shown this flow chart is not visible. It is not coming on this whole screen.
Oh,
can you bigger? Is it possible?
It is at the full screen.
Okay, leave it then. Fine.
No, it is at the full screen. So I mean, I can probably try to enlarge this.
Yeah, now we can, yeah.
Okay. So what is done is the seaweeds are chopped initially or shredded, and sodium carbonate solution is added. I mean, this is a well-known process, so I won't go into details about how it happens, but I'll just go through the steps that are followed for everybody's information. So the seaweeds are chopped, and sodium carbonate solution is, it's treated with sodium carbonate solution to extract the alginate from the chopped seaweed, because sodium forms a compound with alginate or alginic acid present in the chopped seaweed. And it is separated from the residue. So residue is the seaweed residue, which is discarded. And the sodium alginate solution that is produced as a result of sodium carbonate treatment is then further purified. So at this stage, there are two processes that are adopted. One is acid treatment and another is alkaline treatment. So you have calcium chloride. Calcium chloride then substitutes the sodium alginate, so sodium in the alginate solution, and to form calcium alginate fibers. And these fibers are then acid treated with any mineral acid, say hydrochloric acid or nitric acid. And it produces alginic acid fibers. Now, these alginic acid fibers are then further treated back again with sodium carbonate to produce purer variety of sodium alginate. So there are no contaminants in all the other contaminants are removed as a result of this final step to give rise to sodium alginate, which is directly used by the pharmaceutical and food industry. So it is of very high quality, of high purity. The acid treatment is done by similar, so this particular step is eliminated in the acid treatment. So directly you get alginic acid. So sodium alginate is treated with mineral acid to produce alginic acid gel. And then it is dewatered. So the water component of the alginic acid gel is removed. And that gives rise to a thicker gel, which is then treated with sodium carbonate to ion exchange the proton, which is present in the alginic acid stage here, for further purification to form sodium alginate. And this sodium alginate is then again used by the food and pharmaceutical industries or even cosmetic industries. Essentially, the main application of sodium alginate in these three different industries is the carrier of the active material, because sodium alginate is a non-toxic material to human beings. So because it contains essentially carbohydrates and sodium. So sodium is bonded to the carbohydrate complex, which is the alginic acid. So to give rise to sodium alginate. So it is ingestible by humans, and it is non-toxic. So the advantage is taken of the sodium alginate being non-toxic and its gelation properties or ion exchange properties by the pharmaceutical, cosmetics, and food industry to be used as a drug carrier by the pharmaceutical industries or active ingredient in cosmetics, for example, protein-based skincare creams and all such, which I'm not aware of very much. But I think most of the ladies would be aware of these cosmetic products. Even men, for example, they use quite a wide range of cosmetics as well these days. So creams and other things for skin treatment. So cosmetic industry also uses this as the carrier of active ingredient, and food industry as well uses it as a thickener in the soup. So most of the soups will contain sodium alginate in different proportion. And it comes from, I think it originates, the concept probably originates from China, where they have been traditionally using this sodium alginate, I don't know, knowingly or unknowingly, in their soups and cooking process as a thickener to thicken the gravy in their foods. So this is essentially the background of sodium alginate. What we have stumbled over is, and I would like to share this little story with you, I was watching a Master Chef program on BBC television, and that is where I stumbled across this particular material and its properties. And then I did some research myself and found that this is a good ion exchanging material, or it has good ion exchanging properties. And therefore, I decided to marry my interest with the ion exchanging properties of the sodium alginate as a product used by food, pharmaceutical, and cosmetics industry to produce materials of my own research interests. And that's how we started this research in, I think, about 2016 or 15, something like that, with my first PhD, or not first, but first PhD student in this area of exploring the alginic acid or sodium alginate as a medium for producing nanopowders of functional materials. So that is the story, and that is how I started using this material for producing ceramic nanoparticles. So what we did was, this is a very well-known schematic. You can find that in the literature, where the sodium alginate, if you look on this particular slide, it says that calcium chloride treatment here, and in this particular, I'll enlarge this. So calcium chloride is added to sodium alginate. So calcium chloride, calcium ions, they ion exchange with sodium very easily in alginic acid, sodium alginate solution. So what happens during the ion exchange process is that in sodium alginate, it's a runny gel. Sodium alginate is a runny gel because it has got it is a linear it has got linear polymeric chains of glucuronic acid and manuronic acid. So these are the chains of or the squiggly bits are the polymeric chains of glucuronic acid and manuronic acid, and calcium is a divalent. So in the case of sodium, it doesn't form a structure at all when it is present as sodium alginate. It's a runny gel. When you ion exchange with calcium, it tries to bind two different chains, polymeric chains together in this particular region. For example, you see the dots are calcium ions in this, and there are two polymeric chains which are bound together by ionic bonds here. So if you have a trivalent cation, then obviously you will have a third chain joining to share the three cations or three positive charges on the cation to form a structure. And therefore, it gives rise to a thicker gel, basically, because of the viscosity of the gel increases from sodium alginate in the first step to, say, calcium or any trivalent cation ion exchange alginate. So what we did was we ion exchanged the cations with sodium alginate, which formed very spherical beads. So we tried to form spherical beads. Now to get the spherical beads, normally you would get a lump. But to get the spherical beads, you need to squeeze out sodium alginate in the form of spheres. So we use needle and syringe method in the lab to squeeze out the spherical bubble at the end of the needle by squeezing the alginate gel through the syringe and a 16 gauge needle. So we produced the beads and we dried the beads in, you can dry it either freeze drying by freeze drying process or by normal convection oven process, whatever you have. And then calcine the beads at about 500 degrees Celsius. Now, interestingly, the calcination temperature does not change dramatically or significantly if you change the material itself. So from one material to another material, which I'll show you in a minute, it still remains the same, which is a mystery. You know, why it remains same is still not very clearly understood. And once you calcine these beads, dried beads, you get functional nanopowders of the cation that you have ion exchanged. So oxides basically. So you can't get any nitrides or carbides, or oxynitrides, but you can get oxides very easily. So why are we interested in nanoparticles of functional material or functional ceramics by this particular method? There are a number of merits of this particular method, which are listed here. Some of them are high surface area, low temperature of synthesis, which conserves energy and has lower carbon footprint as a result. Enhanced homogeneity, so you get very, very homogeneous material, which you will see in a minute. Easy to control composition during synthesis, because composition during synthesis is determined by the ionic concentration in the solution itself with which you treat. Lower sintering temperature, less energy intensive processing steps, and inexpensive precursors in general, particularly the alginate itself is very inexpensive. However, there are some demerits. Nanopowders have problems in handling. They are, on a large scale. In a lab scale, it is easy to handle, but on a large scale, it is not easy to handle. Toxicity of nanopowders is not very clear. People are still are trying to understand the toxicity of nanopowders of any form or any composition to human beings. So there's significant amount of epidemiological studies that is going on to understand the toxicity of nanopowders. And of course, there are problems of scaling up, which is quite challenging as well, or proven to be challenging. The driving force or driving factors and challenges are listed here. So it's a simple or simplicity of the process, low carbon footprint, probably carbon neutral, I would say, but still to be explored. The alginate process itself, I believe, is carbon neutral, or it could be proven to be carbon neutral, but still not very well understood. It's an environmentally friendly process. It has greater sustainability. However, there are problems with scaling up of the process, and of course, the other advantage is cost reduction because of the cheaper precursors that are used. Okay, so I think this I've already told you about this on this slide, whatever is in the information on this slide. It's a novel method to synthesize nanopowders in a quick, environmentally friendly and cost-effective manner that we have developed using sodium alginate derived from seaweeds. Gelation of alginate is due to the interaction of carboxylate or carboxylic acid groups that are present in the carbohydrates with the metal ions in the aqueous solution. During calcination, the metal ions become immobile and cannot readily. So this is a very important step. If this was not present, then it won't yield nanopowders. But incidentally, during the calcination, the metal ions become immobile and cannot readily come close to each other in the open structure of the alginate ion exchanged beads itself, thereby restricting diffusion of ionic species and hence the possibility of producing smaller nanoparticles instead of coarser particles due to sintering at nanoscale. So, okay, so I will take you now bit by bit from material to material through our journey, how we started and where it has ended up in the end. So we started our first experiment with producing simple binary compound of nickel oxide. Nickel oxide is used in a number of applications, including solid oxide fuel cell in making the anodes of the solid oxide fuel cell. It's also used as catalyst. It's also used as semiconducting oxide material for sensors. And it is also used as one of the components of magnetic spinels, for example, nickel ferrite based spinels or their solid solution. So what we did was we made the solution of sodium alginate. So sodium alginate was kindly supplied to us by Procter and Gamble, with whom we have strong research links in the school. So Procter and Gamble, which is a pharmaceutical giant, supplied us with the sodium alginate material to be used for our research. And then we dissolve that in distilled water. You can also dissolve that in deionized water to be on the safer side. We have tried both and it doesn't make much difference. So the beads, so the solution 1 is the sodium alginate solution. Solution 2 is a nickel nitrate solution. So we made the sodium alginate solution and we squeezed the drops of sodium alginate into nickel nitrate solution. And instantaneously, the beads, they are formed, they retain the shape from the runny gel, which is this one, sodium alginate. When you squeeze out the beads into nickel nitrate solution, it retains the shape in the form of wet beads. And then these wet beads are sieved through the sieves, appropriate sieves, and oven dried calcined to produce nanoparticles or nanopowders. We use typically 16 gauge or 1.194 millimeter diameter syringe or needle, for example, needle to squeeze out the beads, these wet beads. This particular slide shows you the beads that have been sieved containing nickel. So these are the ion exchange nickel beads, nickel alginate beads. And you can see that they are very, very spherical in shape. You see, for example, if I just enlarge this bit, so they are very spherical in shape. So these beads are produced from the runny gel by squeezing the beads out of the syringe. They look green. Normally, sodium alginate is colorless or sort of colorless, whitish gel or pale yellowish gel. But when you ion exchange with nickel, it takes up the green color of nickel nitrate. And when you dry the beads, you get beautiful emerald green nickel alginate sample out of these beads when they are dried in the oven. So this work has been published in Journal of American Ceramic Society. This is a reference here. We published this work. This was the first experiment we did to produce nickel oxide from nickel alginate ion exchange beads. This is my PhD student who started this work and later on ended up staying as a postdoc for 3 more years with me to continue with this work. And now he's back in China. He's I think in one of the universities in Guangzhou or Guangdong province. So after nickel nickel oxide beads, we tried to ion exchange. We thought, look, let's see if it ion exchanges with other cations. So we tried ion exchanging with silver nitrate. So these are the beads of silver nitrate ion exchanging process. These are the beads formed due to the ferrous chloride, FeCl2. These are the beads formed from yttrium nitrate solution. And these are the beads that are formed from zirconium chloride. So you can see that they get beautiful colors. They give rise to beautiful shades of colors. Depending on the cation, you ion exchange. And the calcined, the dried beads are shown here. The colors of the dried beads are shown here. And these beads are typically, these beads are typically about 3 to 4 millimeter in diameter. So they are very porous beads. The structure of these beads is very porous. And this work was then subsequently published in, so we looked at the ion exchange kinetics of the various cations with sodium alginate. And this was then subsequently published in 2014 in Journal of Materials Science. So we tried to calcine the nickel alginate beads at different temperatures for different lengths of time. And you can see that this is the nickel alginate beads, XRD pattern of nickel alginate beads, calcined at 500 degrees Celsius for 3 hours. And as you increase the calcination time, naturally there is a grain growth. So this is in the form of nanopowders. You can see the peaks are very broad. And it's a single phase, very, very pure nickel oxide without any traces of any impurities at all. The peaks sharpen as you increase the temperature, the time at 500 degrees Celsius due to the grain growth. These are TEM images of, I mean, even here, for example, they are still in nanoscale, but they are in the range of around 100 nanometer, whereas here they are in the range of about 10 nanometer to 20 nanometer. So you can see here, these are the TEM images of different nickel oxide particles produced by different thermal history. For example, A, B, and C are at 500 for 3, 6, and 12 hours calcination, whereas D, E, and F are at 700 degrees Celsius calcination for 3, 6, and 12 hours respectively. So these are bigger particles, and therefore they are appearing dark on the TEM images as well, because they become less transparent, and therefore they don't show the planes, lattice planes. Whereas here, if you zoom in, you will be able to see the lattice planes, particularly in this sample A, which is typically, let me see on the scale. It is about, you can see about 20 to 30 nanometers. This is a nanometer marker here, 20 nanometer. And you can see that it's about 20 to 30 nanometer in size, whereas here the particles are much bigger. For example, you can see when you calcine at 700 for 12 hours, the particles become really big. That's a 50 nanometer marker. So it's about 100 nanometer in diameter from corner to corner, I suppose. So why does the does the method produce nanopowders and not coarse powders, even though the calcination temperature is around 500 degrees Celsius, which is high enough for nanoparticles to grow if left to themselves in the form of in a close proximity. So the reason to explore that reason, or to explore the problem or the question, to answer the question, we tried to freeze dry the sodium alginate beads produced by nickel ion exchange. So these are the ion exchange beads produced by nickel ion exchanging process. And these are freeze dried beads. So these two images, the top image, or let's say the first image on the left, A, is a freeze dried bead of nickel alginate. And this has been calcined, sorry, not calcined, this is dried beads, dried bead at about 80 degrees Celsius sorry, these are freeze dried. So yeah, they are not, so they are freeze dried beads. So what you see here is the structure, the external structure of the bead in this particular graph, micrograph. And you can see that there are indentations on the surface due to freeze drying or shrinkage of the bead itself. So originally they were spherical, but due to uneven shrinkage, the bead shape has been distorted and it has been indented. Now, when we did the X-ray microtomography of the freeze-dried beads to look at the internal structure, this is what we see. This is the internal structure, so the cross-section of the bead in A, freeze-dried bead in A. And you can see that there are empty spaces in here. There are lots of empty spaces. So these are all voids. This particular graph, micrograph C and D, are the images of A and B respectively, but taking out the solid or the empty spaces to highlight the empty spaces. So these dark regions here are the empty spaces in these beads. And the veins here are the location where the ion exchange has taken place between nickel and the carbohydrate or carboxylic acid groups. So nickel ions are resting here on these veins, and you can see that there is no path for diffusion between different veins, and therefore that is the main reason why the ion exchange process using sodium alginate gives rise to nanoparticles, even though the calcination temperature is high enough for the diffusion to take place and the grain growth to occur due to ripening process. And this particular research or investigation was then subsequently published in RSC Advances. So it's a Royal Society of Chemistry journal. So we did the X-ray microtomography to understand why the nanoparticles are produced by this particular process. This is the calcined bead. So this one is the dried bead, freeze-dried bead, and this one is the calcined bead. So you can see that this is the calcined bead, and the structure of the bead is still retained even after calcination. So this is the calcined bead retaining the structure, showing the retainment of the structure. And again, the calcination process does not, because it does not break down the structure of the bead, it still prevents the grain growth between the nanoparticles. Okay, so that was the story about nickel alginate or nickel oxide production. Next, we moved on to a little bit more complex material. So we thought, okay, why not add another cation, the second cation, to the solution? So we tried with the aim of producing solid electrolyte for solid oxide fuel cell. We jumped onto the material gadolinium cerium alginate bead production process. Again, the process is same. So we chose two different compositions: cerium 0.9, gadolinium 0.1 oxide, and then cerium 0.8, gadolinium 0.2 oxide. These two materials are very good oxygen ion conductors and therefore find their applications in solid oxide fuel cell as oxygen ion conducting electrolyte. So we decided to to apply the method of sodium alginate process that we developed for producing these nanopowders. Because these nanopowders are very expensive to buy from, say, Aldrich or Johnson Matthey or Fisher scientific companies. So they sell this at a very high cost. So we thought, let's see if we can produce these by our process. So we made the solution of cerium and gadolinium ions in the appropriate ratio. So that is what is the solution 2 here, containing cerium and gadolinium nitrate salts dissolved in water. And then again, the step 1 is same, solution 1 is same, sodium alginate in distilled water. And then we squeezed out the beads of sodium alginate into the solution 2 containing cations, which again, to our pleasant surprise, gave rise to beads. And then this process follows. It's the same process that we have developed for nickel. And we calcined these particles at different temperatures for 2 hours in this particular instance, because we saw in the nickel, with our nickel experience, we found that it produces oxide powders, nanopowders with 3 hours of calcination time. So we decided to move it down to 2 hours. And we calcine instead at 4 different temperatures, not knowing what will happen, whether it will form a single phase. And to our surprise, it did form a single phase, cerium gadolinium oxide at 500 degrees Celsius itself. You can see that the peaks are very broad, but they are the same peaks as the fluoride peaks in the sample calcined at 900 degrees Celsius. And these are the peaks that are indexed from the standard diffraction pattern in JCPDS. So you can see that all the peaks are present, albeit at a lower intensity compared to that at 900, simply because of the tiny nature of the particles produced at 500 degrees Celsius. And you can see that the peak intensity slowly increases as you or creeps up as you increase the temperature. So what we found was, interestingly, that there is no linear relationship between the temperature and the particle size. We found an exponential type of relationship. So initially, the particle size or growth of the particles is much slower. And then suddenly at 700, it takes off exponentially. So up to 700, the growth rate of the particles is much smaller compared to that at 900 degrees Celsius. And the kinetics of grain growth, we published that paper in, or that particular part of the research in Chemical Engineering Journal for the two compositions of the CGO, that is cerium gadolinium oxide. These are the TEM images of cerium gadolinium oxide. We then published the research as well in Journal of American Ceramic Society and Royal Society Journal of Materials Chemistry as well for these two materials by exploring different properties of the CGO produced by alginate process. We also looked at the composition. So while we know that we have produced a single phase CGO, 1 and 2, designated for these two different compositions as a function of temperature, but we wanted to confirm that the stoichiometry of cerium and gadolinium is the one that we started with. So this was the nominal concentration of cerium and gadolinium in the nitrate solution that we used for ion exchange process. And we did the ICP analysis and EDS of using of the TEM particles. So we did EDS under TEM, not under SEM, because SEM you won't be able to see the particles at all. These are tiny particles. So we then decided to do the ICP analysis and EDS analysis to confirm the cerium to gadolinium ratio. And again, to our surprise, the correlation is very good for 0.9, that is 90% mole percent cerium, 10 mole percent gadolinium, is similar to what we got by the ICP analysis, around 91, 92% cerium to about 8 or 9% gadolinium by both the methods, EDS using TEM and ICP, that is induction coupled plasma analysis, which is a gold standard, which is considered to be a gold standard analytical tool for ceramic composition analysis. And similarly, we found a similar ratio, stoichiometric percentages of cerium and gadolinium for this particular nominal composition of 80% cerium, 20% gadolinium in the nitrate solution. Okay, so that was a success story of producing the solid electrolyte, cerium gadolinium oxide solid electrolyte for solid oxide fuel cell applications using alginate method. Next, we tried our luck with ferrite. So we tried to produce nickel ferrite and cobalt ferrite, which are the spinel magnetic materials. Again, we didn't do much of a study on this, but this was just out of interest. We produced these nanoparticles for somebody that is a collaborator of mine interested in measuring the magnetic properties of ferrites of transition metal and their solid solutions. So we produced some of the material for them for the study. And again, the XRD pattern shows that they were all pure phases of nickel and cobalt ferrite produced at 400 degrees Celsius for 2 hours of calcination temperature. These are some of the re-12 refinement parameters that we obtained from these diffraction patterns. And the particles are having negligible strain, and the GOF, goodness of fit, was under 5%, which was considered to be a good fit. And the lattice parameters of these two materials, NFO is nickel ferrite and CFO is cobalt ferrite, matches very well with the reference lattice parameters from the literature JCPDS powder diffraction file. So again, we think that we have produced some high quality magnetic powders. These are TEM images of nickel ferrite on the left and cobalt ferrite on the right, showing you the particle size. This is the 5 nanometer marker. So they're typically around 10 to 20 nanometer in size, showing you very clear crystallographic planes of the spinel lattice, cubic spinel lattice. Okay, so recently we tried to embark upon adding the third cation. So we tried to produce cerium, gadolinium, co-doped with these rare earth elements by alginate process. Now there is a specific reason why we have looked at this particular these materials, and we are actively we got some interesting results, and we are at the moment actively looking at applying these in solid oxide fuel cell as the fast oxygen ion conductors. So again, the process is same. So we have the sodium alginate to give rise to sodium alginate solution. And we have the metal nitrate of 3 different metal ions, cerium, gadolinium, and one of these rare earth nitrate solution prepared in deionized water. So we have used here deionized water instead of distilled water. And then the metal complex solution is added with the beads of sodium alginate squeezed out through the syringe to give rise to wet beads, which are sieved and then dried in oven, finally calcined into nanopowders. So these are the different beads that we have produced of metal ion exchanged. So 3 cations are exchanged in this particular situation. So this is the CGO where cerium and gadolinium are the 2 metal ions, and these are the beads by adding dysprosium, erbium, and holmium to these beads here, cerium, gadolinium, ion exchange beads. These are the dried beads at the bottom. At the top are the wet beads after ion exchanging. So these are oven dried. They're not yet transformed into nanoparticles. But you can see that there is about 50% shrinkage. These are about 4 millimeter in diameter here, whereas down here, the dried beads are about 2 to 2.5 millimeter in diameter. So there's about 40 to 50% shrinkage in the beads. So you can imagine that 40 to 50% is the water content in these beads. And that is the reason why they're highly porous, as seen by the X-ray microtomography images earlier in the talk. So these are highly porous, and therefore they yield, or they successfully yield the nanopowders. So we did the DSC TGA. So these are the DSC standard DSC TGA graphs, basically to find out what is the minimum temperature at which you need to calcine these powders or these beads to produce nanopowders. So you can see that the calcination temperature is somewhere around 400 for all these four different compositions. That is cerium gadolinium oxide, and then cerium gadolinium oxide co-doped with dysprosium, erbium, and holmium. So as I said before, the calcination temperature surprisingly does not change very much in spite of the change in cations that we try to ion exchange with. Whereas in the solid state, if you try to adopt a solid state method to make these nanopowders, you will need to calcine at significantly higher temperatures to form a solid solution, because you need to be able to dissolve cerium oxide into gadolinium oxide and then dysprosium oxide. So if you choose three different oxides and if you ball mill them together to produce the solid solution, such as CgO doped with dysprosium, erbium, or holmium, then you will require at least, I would say, 900 degrees Celsius to form a solid solution of oxides, or even higher sometimes. And the cost of raising the temperature to form solid solution is the coarsening, and therefore you lose the ability of the method to produce nanopowders because of the coarsening process that is taking. So you're fighting against the two opposing forces. One is to keep the size down to form the nanopowders, whereas the other force is to you're fighting is the increment in the size of the crystals as a result of higher temperature. And these two forces are opposing each other, and you can never win. You will have to eventually, if you start with the solid state method, you will have to the material will have to undergo high energy ball milling in order to produce nanopowders. And certainly you will have to then worry about the contamination of the powders because of the high energy ball milling from the container in which you are ball milling, or the media that you use, the balls that you use to ball mill the nanopowder, to ball mill the powders. Okay, so this is the SEM image of the CGO. So CGO co-doped with dysprosium, erbium, and holmium from the beads that are calcined at 500. So the top line is for 500 degrees Celsius for 2 hours, and the bottom line is for 700 degrees Celsius for 2 hours. And you can see that there is a high degree of porosity in all these calcined beads. And that is one of the reasons why we believe strongly that the method gives rise to the nanopowders instead of coarse powders, and therefore doesn't need ball milling at all. It just needs breaking up the agglomerates to form the nanoparticles, which is the main advantage of this method. So this is again the SEM image of CGO, cerium gadolinium 0.8 doped with dysprosium and erbium and holmium, calcined at 500 degrees Celsius and 700 degrees Celsius. Again, showing you the extent of porosity. I think I've got it probably wrong. This looks more like 700 degrees, and this looks more like 500 degrees SEM microstructure, because this is more porous compared to this one. So then we did the re-12 refinement of the powders that we produced by at two different temperatures. So this is at 700, this is at 500 degrees Celsius. And again, it gives rise to a very good fit. You can see that the residuals are very, very small at the bottom. And that confirms that the fit is excellent. compared to the standard pattern. We did the retwell refinement and yes, I think the match is very good with the standard pattern. We also looked at the D-spacing. So these are the D-spacing for different planes. These are the HKL values of different crystal planes. And we looked at the D-spacing from XRD pattern or from the retwell refinement pattern. And we calculated from TEM as well. So from the TEM, these are the TEM images of 500 and 700 degrees Celsius on the right. The spotty image here of 700 degrees Celsius clearly indicates that there is a crystal growth at 700 degrees Celsius compared to that at the diffuse ring pattern that you see for 500 degrees Celsius product. And what you see here is the XRD data or the interplanar spacing for different planes, HKL values of different planes, matches very well with the TEM data. Of course, the XRD data is much more resolved compared to TEM. And TEM, there'll be greater error in TEM measurement compared to XRD for obvious reasons. Again, so these are the, so this is for the gadolinium, CGO. GD is highlighted here. So this is for CGO. This is for dysprosium co-doped. So DY is highlighted here. So CGO is co-doped with DY. And you can see again that the XRD and TEM images, interplanar spacings, they match very well. And also the retwell refinement shows that the residuals are bare minimum. So indicating that the fit is excellent between the data points from XRD and the calculated fit from the retwell refinement. This is highlighting erbium. So this is the erbium compound. Again, erbium co-doped CGO, which again shows a very good fit with the XRD pattern. And finally, this is for holmium as well. So I've shown you all the three co-doped plus the original CGO. And again, the fit is very, very well demonstrated between the calculated pattern and the raw data from the XRD. So we published part of this work. So holmium compound, holmium co-doped material was published in 2018 in Acta Crystallographica C, where we looked at the change in lattice parameter as a function of average cation radius, and it almost follows a Weygard's law, except for point C here, which we don't know why it has deviated from the Weygard's law, but it could be a negative deviation from Weygard's law due to the, so with this needs to be still investigated. So we are still looking into that. Okay, so so far I have shown you the results of producing nanopowders of functional ceramic materials containing 4 different cations, starting from single cation, nickel oxide, to doping with 3 different cations, sorry, not 4, 3 different cations in this case, using the alginate bead process. So we were thinking, you know, why can we avoid making beads altogether and use any other method, not changing very much, but making it or simplifying the production process itself. So we tried to use the granulation process. So alginate powder was granulated in a pan granulator to different granules shown here at the bottom. So this is the tiniest granule, and this is the largest granule. So we used, instead of sodium alginate gel, we used sodium alginate granules, because making granules is much more easier and simpler process compared to making the beads, which is more labor intensive process. The rest of the process remains the same. So instead of using sodium alginate gel, we have used here sodium alginate granules to produce nanopowders. And to our surprise, it doesn't make any difference. It doesn't make any difference. So this is CGO, pure CGO, so cerium gadolinium oxide, calcined, so produced using sodium alginate beads, and that is using sodium alginate granules. So this is the bead process. The red trace is from the granule process. So granulation also yields exactly of identical purity and crystal structure for various compositions. So we are actually researching into now using granules as well, along with the beads, to produce the functional nanomaterials, oxide nanopowders. This is the re-12 refinement of the material that is produced from alginate granule process. And you can see that the residuals, again, for the 4 different compositions are very, very tiny, indicating very good fit with the XRD pattern. So I was saying about the applications of these materials. They are essentially in the solid oxide fuel cells as the oxygen ion conducting membrane. So this is the solid electrolyte, which is in the solid form, impervious solid state material. This is the cathode material, which is exposed to oxygen or air. And this is the anode material, which is exposed to the fuel. So the oxygen ionizes here, reduces to oxide ions, and then migrates through the oxygen ion conductor to come here. Protons are produced here from hydrogen, oxidation of hydrogen to protons, and protons then combine with the oxide ion to produce H2O and the power that is produced. So this is how the fuel cell, simple fuel cell works. And our aim is to, well, we are actually researching. I've got 2 new students, PhD students, one of them working on new cathode materials, and the other one working on new oxide electrolyte materials. And we'll be testing the fuel cell, or that is the plan, towards the end of their PhD research, or in the final year of the research project. So this is the TM of one of the TM images of one of the co-doped material, that is holmium, co-doped with cerium gadolinium oxide. And there are different compositions. So HO5, 10, 15, and 20% mole percent of holmium co-doped with within the cerium gadolinium oxide. So again, these are produced by the alginate process, ion exchanging alginate process using beads. And again, the important aspect is that the powders are very, very fine, and tiny nanoparticles are successfully produced of different compositions, 5 different compositions here. Interestingly, the sintering temperatures, because they are nanopowders, is brought down quite significantly. We have been able to sinter these nanoparticles to full density, almost 99%, 98 to 99% density, theoretical density, at about, I think, 1100 or 1200 degrees Celsius compared to the conventional sintering temperatures of in excess of 1500 degrees Celsius. And you can see that the material is fully dense. These are the grain boundaries, and these are the grains, CGO co-doped with holmium grains. And there is a uniform distribution of elements in the in this sintered structure. These are the X-ray maps. And this is the combined X-ray map of all the elements, that is oxygen, holmium, gadolinium, and cerium. And you can see that the uniformity of the distribution of these elements in the matrix is clearly seen. These are the X-ray patterns, XRD patterns of different compositions. And we did the impedance spectroscopy as well. Impedance spectroscopy is a very powerful tool used normally to by the electrochemist to look at the ion migration or ion dynamics in the material. And what you see here is one of the spectra, impedance spectra, at one particular temperature. The circles, open circles, are the raw data points, and the solid line is the fitted equivalent circuit here to the data points. And you can see that the fit is excellent. And the frequency range is from about 1 Hertz to about 1 megahertz. Although our instrument can go from microhertz to 32 megahertz, we have measured only up to 1 megahertz. And the lower end, we have measured only from 1 Hertz, because otherwise it takes a very, very long time to acquire the data. Okay, the important matter is after fitting the data, you extract the parameters, that is the resistivity and the capacitance or CPE values from the fit data. And the resistivity is then used to obtain the conductivity from the dimensional parameters of the sample. So this is the recent paper by John Goodenough, and his group in University of Texas in Austin, which was published in 2014. And in this particular article, they have reviewed some of the best oxide ion conductors. Now, all of you will know John Goodenough because, I mean, if you are a solid state electrochemist, then you would know John Goodenough, who won the Nobel Prize for chemistry a couple of years ago for his research into oxide ion conductors or ionic conductors for battery applications. So, so yeah, I think so. John Goodenough is a very famous and reliable name in the solid state electrochemistry area, and you can see that some of the review or the materials that have been reviewed shows that the best oxide ion conductor is SNS. SNS is the silicate compound, which has the best oxide ion conductivity compared to some of the others, which are LSGM, GDC, that is gadolinium doped ceria. LSGM is lanthanum, strontium, gallium, manganate. Yttria stabilized zirconia. So these are some of the competitor materials, and SNS has come out to be the one with the highest oxygen ion conductivity. If you look at the y-axis here, the highest ionic conductivity obtained is about 10 to the, or ln sigma T is about 4 at about 700 degrees Celsius. Okay, so that is the temperature in Celsius on the top axis. And that is the ln sigma T, which is about 4 or maybe 3.5, I would say. Let's say 3.5. Okay. This is our material. This is our material produced by alginate method. And what you see here is that in our case, ln sigma T at similar temperature, 727 degrees Celsius, is about 6.5. So you can see that our material produced using alginate method has better properties, or at least 2 orders of magnitude higher ionic conductivity, oxide ion conductivity, compared to the best known material so far in the literature. So this is what we are exploring at the moment, why there is a difference of 2 orders of magnitude compared to some of the competitive materials. Okay, next, I would like to, I think it is almost coming to time. I think 5 minutes to 11 here, which is probably 5 minutes to 3 out there. Is it? No.
Yeah, it's okay. You can carry on for another 10 minutes. No problem.
Okay. So 3:30, I think, isn't it there? 5 minutes to 3:30. So I'm conscious of the time. So I will try to swiftly go through the remaining slides, and maybe I think I might have to skip some of the slides as well, if need be. So we looked at LSCF as well. So we had looked at 4 different compositions of LSCF. LSCF is lanthanum, strontium, cobalt ion, or ferrite, which is commonly used as cathode material in solid oxide fuel cell because of its high catalytic activity for the reduction of oxygen. And also it is a mixed ionic conductor as well of electrons and oxygen, so that it interfaces better with the electrode, with the current collector leads. So we made 3 different compositions of LSCF using alginate bead method. And you can see that the beads are produced, or they are very similar to what we produced earlier. These are the sieved dried beads, and these are the calcined powders of LSCF. I'll see if I can play this video for you to just understand how the, okay, I think the video has turned sideways for some reason on this slide, but that is the beads being stirred in the alginate, the ionic solution, the alginate beads being stirred in the alginic, in the cation solution, nitrate solution, during the ion exchange process itself. They are very free flowing beads in the alginate beads in the cation solution, which is quite fascinating actually to me, or to us, that they don't stick to each other, and they form nicely separated beads in every single instance. So the consistency of the process is phenomenal. Then we did the DSC TGA of these beads, LSCF, 3 different composition of LSCF. And again, what you find is that around 400 degrees Celsius is the temperature at which the fully oxidized product is formed, single phase product is formed. So irrespective of the cations that we ion exchange in alginate, the alginate process produces the single phase product at around 400 to 500 degrees Celsius as the calcination temperature. So if you look at this, so these are the three different compositions that we produced. And again, these three compositions, they form a very nice single phase product from the alginate process. So again, showing that it goes to show that even if you add 4 different cations, in this case, lanthanum, strontium, cobalt, and iron, 4 different cations, it still gives the same product quality. The product quality is amazingly good from this alginate process. So these can be used in electrochemical sensors as well. And so these are potentiometric sensors. I won't go into details about these applications because of the lack of time. But we did some studies on using these materials, specific materials for nitrogen oxide gas sensing. And you can see that this is the mass spectrometer trace of change in concentration of nitrogen dioxide going up and down. And this is the trace from the sensor, which is very good. It matches very well with the with the mass flow controller, rather not mass spectrometer, mass flow controller trace, where we have changed or stepped up the composition of nitrogen dioxide in the gas mixture, and here step down. So while stepping up, the sensor response is very quick, and it gives rise to a stable response fairly quickly and consistently in both directions, stepping up the concentration and stepping down the concentration. On the left, you see the measurement setup that we have used for our data collection and gas train here. Yeah, I think I will probably skip this slide, but the results are, nitrogen dioxide sensor results have been published in Analytical Chemistry, which is an ACS journal, American Chemical Society journal. So we published this data. So if anybody is interested in this piece of work, then they can refer to this paper in Analytical Chemistry. Similarly, this shows the response from the sensor. So we have spiked the sensor with the nitrogen dioxide for several times, and we have recorded the response, and you can see that the response is fairly consistent from the sensor. And this particular graph on the right shows the response time, which is the for stepping up the gas concentration. The response time is about 8 seconds, and stepping down is around 10 seconds to come back to the original value. Okay, so that is fairly that is excellent. I think 8 seconds and 10 seconds is fairly good. So this is about the carbon monoxide sensor that we have tested. And again, similar results have been found for carbon monoxide sensors. What we have also found is that the response of the carbon monoxide sensor can be influenced by the electrode kinetics, electrode composition, electrode morphology, and electrolyte composition. So we have analyzed all these 4 different parameters, and that analysis of, or the results of the analysis, was published in Sensors and Actuators, 2 different papers or publications in Sensors and Actuators B from my research group. Similarly, we looked at a different electrolyte, barium lanthanum oxide electrolyte, which is again a very good oxygen ion conductor, barium lanthanum indium oxide. And we published these results as well in Analytical Chemistry, which is again an ACS journal some time ago. Okay, so I think I've got now last few slides. I think 4 or 5 slides are left for me to conclude. So please bear with me. I might just go over by about few minutes. So my apologies for that. So cost analysis. We did some cost analysis as well of the process that we have developed. And this was what we came up with. So what we found was that there's about 70 mass percent loss of alginate during the heat treatment. That is during the calcination of the beads, and the mass of sodium alginate required to produce 1 kilogram. So we scaled up our process basically for this calculation from grams to kilograms. So we produce only in a few 10 grams in the lab. But if you want to market this process, then you should demonstrate the scalability as well, and also the cost effectiveness during the scaling process. So we did this cost analysis, and what we found was that to produce 1 kilogram of cerium gadolinium oxide nanopowders, you need about 3.33 kilograms of sodium alginate, which is about 216 pounds from the commercial supplier. Hence, the total cost to produce 1 kilogram of CGO is 782 pounds for CGO1, that is 0.1 gadolinium, and this is for 0.2 gadolinium, 906 pounds to produce 1 kilogram. What is marketed in the so this is the market price for that sorry, I think I got it wrong somewhere. Well, I think I'll have to probably work it out myself later on to convince you. But the profit margin, what we calculated, was about 400 to 500% if we look at the market price of, okay, yeah, that's the market price. Yes, that's the market price of CGO, 4,680 pounds per kilogram. Okay, whereas what we got was 782 pounds for CGO1 and 906 pounds for CGO2. So you can see that there is so much of difference between the price value, even at the of CGO2, if you compare of CGO2 with the market value. So this is from the alginate process, and this is the market value from the commercial supplier of CGO. And you can see that straight away, there is about 400 to 500% of profit margin in this particular, or using our method to produce CGO1 and CGO2 compared to the market estimation or market price. Okay, similarly, we try to work out the YSZ as well, that is yttria stabilized zirconia. The nanopowders of yttria stabilized zirconia will cost about 1,355 pounds per kilogram, whereas our method will give you at 466 pounds per kilogram. And similarly for nickel, YSZ, that is anode material, or LSM, YSZ, which is the cathode material, again, there is significant price difference in the market price and what we calculate from our product process. Scaling up again, to conclude, scaling up of this process is one of the main challenge in developing this process technology. Scaling up of the process technology is a multidisciplinary problem, engineering problem, and we are working on it at the moment with some of the chemical engineers and mechanical engineers in University of Leeds to come up with a plan design or process flow diagram for making this nanopowders at an affordable cost. So finally, last two slides, I think. So the message I would like to like you to take home at the end of my talk is you need to think, I mean, how we stumbled across this process is by thinking outside the box. So you need to think outside the box to introduce novelty to your research. Hybridization of ideas through collaboration is very important, because if you collaborate with people of different skills, then that will definitely lead to a novel outcome. Be brave and try out new things in research. You will either you'll be either successful or you will fail in your experiment. You have at least 50% chance of being successful. So looking at the positive side, you have at least 50% chance of being successful. And if successful, naturally the rewards are immense. Thank you for listening. And I would like to acknowledge some of my collaborators and people who have worked with me and who have funded my research in coming to this particular stage in last few years. Thank you very much for your attention. And yeah, I apologize to keep you 10 minutes longer than expected for this particular session. I'm open to any questions if you have. Thank you very much.
Any questions? The house is open for the questions. Yeah, Digvijay Singh, I will unmute you and then you can. Yeah, you can ask your question.
Thank you, sir. Thank you for the question. Thank you for this session and this such a nice lecture. Sir, my question is, what about the stoichiometry of the product? Like you are showing that there is a C minus delta. Is it due to the some salt synthesis and some other process, like in molten salt synthesis process? Is it produced due to the use of salt?
Sorry, I could not get your question because your voice was breaking.
Now I'm audible.
Yes, you are audible. Yes.
Okay. Sir, my question is regarding stoichiometry of the product. As you showed that the end of the product, you have oxygen C minus delta.
Yes, yes.
So why this comes?
That is because of the oxygen vacancy present in the oxygen vacancy present in the material itself, because these are all oxide ion conductors. So when the so for the stable structure, you need those oxygen ion vacancies, and therefore normally these are all oxygen deficient compounds. Does that answer your question?
Yes, sir. Basically, sir, I want to know, is this effect of using sodium jalconite, like if we go through the process like molten salt synthesis, there is a same kind of thing is present regarding stoichiometry, and this is due to the use of salt. So this is due to the use of sodium jalconite.
Sodium zirconate. I'm not familiar with sodium zirconate material as such, but molten salt synthesis inherently. So what is your question actually? What is your question?
So it's again, why this change in the stoichiometry, like oxygen C minus delta?
Yeah, I mean, I'm not familiar with sodium zirconate. I have a feeling that sodium zirconate is not an oxygen ion conductor.
Yeah.
It is probably a sodium ion conductor, more of a sodium ion conductor. Is that correct?
Yes, sir.
Yeah. So so do you see oxygen? Do you mean to say that these materials are also oxygen deficient, sodium zirconate?
Yeah, sir. In molten salt synthesis, by using salt of sodium or salt of potassium,
Right.
such things are present also there. So
yeah, I think because it's a sodium ion conductor, maybe it will have sodium ion vacancies. And that could be probably balanced by the oxygen non-stoichiometry as well, because your material needs to be charge neutral. So maybe that is the reason why you might have oxygen deficiency in sodium zirconate itself. Also, I think you should see, you should try to see if there is oxygen non-stoichiometry by annealing your material in oxygen-rich environment, and see if that saturates with the oxygen or it removes the oxygen deficiency.
sir, this also affect the conductivity or resistivity of the ceramics. No?
Yes, it will affect. Yes, it will affect the conductivity or resistivity, as you say, of the ceramic material, because defects will contribute to the ionic movement in the lattice. So yes, it will affect the ionic conductivity, or if that is what is of interest to you for with respect to sodium zirconate.
So there is an effect on structure.
Structure, I think structure not so much. I believe if the if there is a small change in the oxygen non-stoichiometry, structure may not. But if there is a major change, then yes, there will be structural instability introduced due to the oxygen enrichment.
Sir, one more basic thing. Sir, this also produces porosity on the surface.
Porosity on the surface. I mean, porosity will be there. Yes, on the surface, there will be greater oxygen loss compared to the bulk if it is a sintered material. So porosity, surface inhomogeneity may be there, but I think you need to produce this material, under different conditions, and analyze it with appropriate tools to understand the effect of various parameters, or effect of changing various parameters in the process of synthesis and manufacturing of components from the powders.
Okay, sir. Thank you. Thank you very much.
Okay, thank you. I
Any
hope I
other
have answered your questions properly, because I'm not familiar with the material at all. So
this is my question. How should I know if this is the correct answer or not? That's why I'm asking you, sir.
I know. So this is my concern as well. Because if I was familiar with the material, then I can confidently say, but because I'm not familiar with the material, what I know about sodium zirconate is from the research that I did during my PhD days, which was 30 years ago, or around that, on Nasicon.
Okay. So
And
actually, basically, I'm bothered about the porosity and the effect of porosity on the conductivity and other physical characteristic of the ceramic.
of course, porosity will have very dramatic effect on conductivity.
Yes,
If your material is porous, then it will be, it will affect conductivity quite dramatically.
yes, sir.
That I can confidently say. But I don't know about the oxygen non-stoichiometry. How significant will be the effect? Yeah.
That's why I'm asking this thing, sir. Does this affect the porosity on the surface or not?
Yeah, I think porosity will be will have significant effect. That much I can say, but I don't know whether your processing conditions will make it more porous.
Definitely, sir. Definitely. The heating conditions and condition of calcination and sintering both.
Yeah. So I think you need to vary the conditions and look at the effect of that as part of your research.
Yes, sir. Thank you, sir. Thank you once again.
Okay.
Any other question? Any question? So if there is no question, we would like to thank Dr. Kale, who elaborated in detail how this sodium alginate or the alginate process is to be used for producing ceramics and other oxide materials. And he also explained in detail about the merits and demerits of producing the nanoparticles through this route, the driving factors and challenges which underlie in this process. And he also explained this process, how he employed this process for producing different types of nanoparticles such as sodium alginate beads, and then CgO, NiNCO ferrite, gadolinium codope, DY-ERHO, and many more. And also he talked about how they can be used in the electrochemical sensors and electrolyte cells and SOFCs. What was the cost overview for the production of CgO powders, and many more. The most important thing for this type of process is that they are quite environmental friendly and they are quite cheap, which makes viable for mass production. That is a challenge, as Dr. Kale was saying. I don't know how much he has progressed in that.
It's the work in progress at the moment.
Yeah. So because if you're successful, then it's a great thing to do that. You are getting a very cheap process to make materials which are environmental friendly also.
Yeah.
So I extend my heartfelt thanks to you for giving your time for this. And on behalf of my college, my colleagues, the faculty, there are many more faculty who are from different universities of Bihar and then different universities of the country itself, because it is a national event which is being organized by AICTE, Government of India. So on behalf of everybody, I thank you all. Thank you very much.
Thank you very much for inviting me, and I really enjoyed participation in the Zoom meeting. Yeah, I think it was a good experience for me as well. Normally, we don't use Zoom for meetings. We use only Teams. But it was a new experience for me, and I think it worked very well.
Yeah, it worked excellent. It was excellent.
So I think I have learned something as well in the process.
Yeah. So thanks a lot. Thank you.
Okay. Thank you very much. Bye-bye.
Bye. The participants are, we will be now finishing this today's class. All the 3 sessions are finished.